Chapter 5. Chapter 5 is all about integration. Another word for integrating is to find the antiderivative. And it's all about an area under a curve. So rather than get caught up in the definitions and the limit definitions in those problems, we are going to take a more conceptual approach so that you have a better idea of what exactly it means. So we're going to start off with how much snow is on Janet's driveway. The weather forecast for January is a snowy one. At midnight there are 80 cubic feet of snow on Janet's driveway. Snow accumulates at a rate of 50 cubic feet per hour. At 6 a.m., Janet wakes up and starts shoveling. Will she be able to make it out of her driveway in time? Let's begin by thinking, how much snow is on Janet's driveway at 6 a.m.? Well, it said at midnight there are already 80 cubic feet of snow, so we're starting off with that 80 cubic feet. Plus, it accumulated at a rate of 50 cubic feet per hour. So it accumulated at 50 cubic feet per hour times the number of hours from midnight to 6 is 6 hours. So we have 80 plus that 300, which means there was 380 cubic feet of snow on her driveway when she woke up. Between 6 and 7, Janet shovels at a rate of 125 cubic feet per hour. Between 7 and 9, she got a little bit tired, so she slows down and shovels at a rate of 108 cubic feet per hour. For part A, I'd like you to pause the video and see if you can write a piecewise defined function for j of t for the hours between 0 and 9 that gives the rate of change of the volume of snow on her driveway, t hours after midnight. For the first 6 hours, the rate of change is a steady 50 cubic feet per hour. For the hour from 6 to 7, it's still coming down at 50 cubic feet per hour, but she's shoveling at a rate of 125 cubic feet per hour. So it's actually, the rate of change is actually a negative 75 for the hours between 6 and 7. Then she slows down, but it's still coming down at 50 cubic feet per hour, but now she's slowing down and she's only shoveling at 108 cubic feet. So the actual change is, its accumulation is negative 58 from the hours from 7 to 9. Now I'd like you to go ahead and pause the video and graph that piecewise function. And hopefully this is the graph that you were able to come up with. For number 3, when is the amount of snow on Janet's driveway decreasing, and how do you know? Well, if we just think about the information that was given to us up here in number 2, it's going to be decreasing between 6 and 9 because it's falling at a rate of 50 cubic feet per hour, but she's shoveling it at a faster rate. So it's falling at a less rate than at which she is shoveling. How much snow is on the driveway at 7 a.m.? Well, again, we can't forget about the 80 cubic feet that we started with. Plus, we have 50 cubic feet for 6 hours. And then we're subtracting 75 cubic feet because she's shoveling for 1 hour. When we do all this math, what do you notice about 50 times 6? Well, the height of this rectangle is 50, and the length of this rectangle is 6. So the area of that rectangle is 300. The length of this rectangle is 75. Negative 75, and the width is 1, so that's how we get that minus 75. The 80 we already started with. This is going to give us a total of 305 cubic feet of snow. And how much snow is on Janet's driveway at 8:30 a.m.? Again, it started with 80 plus 50 accumulated for those 6 hours. Then we subtracted that first hour at a rate of 75 cubic feet per hour. And then the second hour and a half, because we're going from here all the way over to an hour and a half, but that rate was negative 58 times that 1.5 hours. And again, if we do all the math in here, we're going to realize that there's only 218 cubic feet of snow on the driveway at 8:30. I'd like to take a look at what each of these mean in terms of our drawing up here, in terms of our graph. The snow is decreasing. The snow is decreasing between 6 and 9. If you notice, our function is less than 0. so it's going to have a negative area. Snow is decreasing. Our function is below the x-axis. If we notice here, other than that 80, the amount of snow on Janet's driveway is 80 plus the area between the curve and the x-axis. For that amount of time, between 0 and 7. And again, it's the same thing here. It's 80 plus the area between the curve and the x-axis for that amount of time. And again, the area underneath the curve, area below the x-axis, is going to be a negative area. And so this is going to lead us to our important ideas. First of all, the accumulation of a quantity is represented by the area underneath its rate of change or derivative curve. In other words, the area between the curve and the x-axis. Number 2, the accumulated quantity is the first rate times the time plus the second rate times the time. That was like the snow accumulating at 50 cubic feet per hour times the amount of time and her shoveling it. So that's what that one means. The third one, and I think this one sometimes can be the most helpful in actually understanding what's going on, is that the units for the area underneath the rate of change curve is the units of the rate of change times the units of the independent variable. On our snow example, we had the rate of change of cubic feet per hour times the number of hours. We see that those would cancel, and so that's how we end up with the total cubic feet. And finally, any area above the x-axis is considered a positive area. It's a positive accumulation, and the quantity is increasing. And any area below the x-axis is considered a negative area. So there's negative accumulation, or the quantity is decreasing. I would really like you to pause the video at this point and try to do these two problems on your own. There's really only going to be one additional problem for your homework, so I would challenge you to try to do these problems, though I will be coming back and doing them on the video. So to start with, a squirrel starts at building A at time 0. It travels along a straight wire connected to a building B. For t between 0 and 18, the squirrel's velocity is modeled by the piecewise linear function shown, where v of t is in meters per minute and t is in minutes. At what time in the interval 0 to 18 does the squirrel change direction? And give a reason. The squirrel changes directions at t equals 9 and t equals 15. At t equals 9, the velocity changes from being a positive to a negative, and t equals 15, the velocity changes from being a negative to a positive. A slight pause for a second. If you think back up to number 3 up above, units for the area beneath the rate of change curve, my y-axis is a velocity, which is meters per minute, and my x-axis is, my independent axis is time, so I'm multiplying this by the number of minutes. Therefore, any area I find is going to be the number of meters that that squirrel has traveled. Part B, at what time is the squirrel farthest from building A, and how far from building A is the squirrel at this time? Well, so we need to consider when my velocity is equal to 0, which is when t equals 9 and t equals 15, and we also have to consider the endpoints. So we need to determine the position. So we're going to make a t-chart, and we're going to find out where is he at time 0, 9, 15, and then my endpoint of 18.